I've been working on this project about visually explaining transformers. As he said, I love visually explaining all sorts of things, usually in math, but I'm happy to stray into the adjacent fields. The target audience here is always a little bit tricky, because I know many of you are engineers and are quite technical, but I don't necessarily want to assume too much background from people. The one thing I will assume is that you're maximally curious, that you're hungry to dig into the details of what's going on. For example, I think most people know that large language models consume a lot of computation. They take a lot of resources. And anybody who has looked at the market cap of NVIDIA recently will also know that they tend to be run on GPUs because they're very parallelizable. One of the things I would like you to come away from this talk with is a deep-to-your-bones visceral sense for what those actual computations are, what the number crunching happening is, and why it's so conducive to parallelization, which is one of the big reasons for the success. So transformers were introduced in this now very famous paper called Attention is All You Need from 2017. And that paper was focused on a specific use case of machine translation. You might imagine it used for Google Translate and things like that. But since then, it's seen a flourishing in all sorts of other tasks. It's not just useful for machine translation, but it's good for transcription with tools like Whisper. It's good for going the other way around, having tools that will take in a piece of text and synthesize speech. It's even good for image classification. It's a remarkably flexible framework. But the model that you and I are going to focus on today, which is the kind that underlies chatbots, is a little simpler than the one that they introduced in that paper. The model is going to be one which is trained to take in a piece of text and then predict what comes next. So for example, here, if you feed it the text, "To date, the cleverest thinker of all time was," it's going to predict from its vocabulary what the word might be. But it doesn't just give a single prediction, it assigns a probability distribution to all possible snippets of text that might come next. In this case, there's a lot of possibilities for what it might be, so it has a relatively spread out distribution over a lot of different things, including some equivocation, recognizing it's going to use the words like probably or undoubtedly, arguably, that kind of thing. If you have a model that does this, that simply predicts what word comes next, you can turn it into something that'll generate new text simply by having it randomly sample from that distribution. You have it look over and weight it according to the probabilities that it gave, sample some word, tack that word onto the input that it was processing, and then run this extended version all through the process again, saying, okay, now that that word's on it, what do you predict will come next? Runs through the whole thing, which takes quite a lot of resources. And then again, it plays this game of sampling from that, tagging it on, and repeating. Now, a lot of people will ask why you would ever have it choose something that's not the most likely word if it generates that. You absolutely can do that if you get into the notion of something called temperature. This will come from assigning the temperature equal to 0. The answer is just you get very stilted outputs that sound kind of trite, and you get a little bit more creativity sometimes, or something that just sounds somewhat natural if you introduce that spark of randomness into it. Now, if you want to turn this into a chatbot, something that takes seed text and then extends it, the simplest way you could start for that kind of project would be to have your seed text establish an environment of a user interacting with some kind of hypothetical helpful AI assistant, take the user input that they typed into your chatbot website, tag that on into this input, suggest to it that what's about to be generated is whatever that hypothetical AI assistant would say, and then have the model start to generate those, again, one word at a time. Really one token at a time, but we'll get into that in a moment. So in this case, I took a relatively simple model and have it provide some suggestions for what to do while visiting Munich, and it goes through and does this random sampling process. And I'll leave it to you to judge whether or not its suggestion seems reasonable here. But it's kind of surprising that this should work, I think. That the act of having something that simply predicts the next word would get you something that seems to have long-range thinking. And some of that comes from the way that it's doing that prediction and just how long-range the associations can be. So what I want to first do is show a high-level sense for how data flows through this whole model. We're not going to go into the details yet, but we will. Just how does it flow through? And then we'll dig into some of the things that I think are required to get that nice visual intuition we want to go for. So when it's faced with this task, it's given a piece of text, wants to predict what comes next, and the text could potentially be quite long, but I'll just show what I can fit on the screen. The first step is to subdivide it into little pieces. And we call these pieces tokens. In the case of text, they're very often words or little pieces of words, sometimes punctuation marks. But one thing to keep in mind is that this doesn't necessarily have to just be with text. Tokens could also include little snippets of an image or little snippets of a sound if images or sound are somehow part of that input. Or if you're creating a different model that's doing a different task, like transcription or image processing. And the process there roughly looks like subdividing it into little pieces and then having some sort of vocabulary of what all possible little pieces are. Now, in the case of text, one little question that might be worth having in the back of your mind as we go through this is to ask, why not just break it up into characters? That seems like a much more natural choice for what the atomic unit of text would be, to break it into characters and then do whatever we're about to do with tokens there. And I just want you to think about that. So we're going to go through, and I'm going to return to this question. But as we do, think to yourself, what would go wrong? Why wouldn't this work well? Or maybe it would work well if we broke it into tokens instead. Broke it into characters instead. The first thing that happens, you have to know something about what happens to be able to answer that question. The very first thing is to associate each one of those tokens with a long list of numbers. And if we think of those lists of numbers as vectors, we'll call it the embedding of the token. And you want to think of those lists as somehow encoding the meaning of each one of those tokens. And at this phase, it's essentially just a lookup table. Each particular token is always going to be associated with the same vector each time that you run it. But the first thing that happens is that you pass that through this all-important attention block, the thing that we're going to spend the second half of this talk digging into, which lets those vectors talk to each other in a certain way and pass information back and forth between one another, so that one that might have just started by encoding a given word might end up taking into account some of its context. For example, sometimes words can be ambiguous. If you take the phrase American shrew mole and the phrase 1 mole of carbon dioxide and the phrase take a biopsy of the mole, you and I read those and we understand the word mole means something fundamentally different in all three of those cases because of the context. So you want to give the machine a mechanism by which it can let words talk to each other so that that meaning could get updated. But it might not just be disambiguating the meaning of a word. It might be that you want to bake some sort of substance or essence of the entire context that's somehow relevant for predicting what might come next into a single one of these vectors. Because what happens here is it doesn't just go through this one attention block, but it's going to flow through many different iterations. So the next thing it passes through has kind of an overly fancy name. It's called a multi-layer perceptron. It's the simplest kind of neural network. When you break it apart, it looks like a couple matrix multiplications with a little nonlinear something sprinkled in between. I won't go into too many details on this particular block, but the one thing I'll say is the majority of model parameters actually live in this multi-layer perceptron. Despite the title, attention is all you need, in a sense of counting parameters, it's about 1/3 of what you need. And if you want to ask, okay, why? What's going on with these? It's a little hard to say. The question of interpreting any of this is a bit of a challenge, but there was some fun research put out by a couple interpretability researchers from DeepMind in December where they were studying where facts like associating athletes with their sports live inside a model. So if you have it autocomplete a phrase like, Michael Jordan plays the sport of blank, if it successfully predicts that basketball is the most likely answer, that answer was nowhere in the context. It couldn't just have come from passing information back and forth between tokens. It has to mean that somewhere inside the parameters of the model that it learned during the training process, it somehow encoded the fact that Michael Jordan plays basketball. And they did a study where they were doing a whole bunch of associations between athletes and sports and trying to probe at the network to figure out where that probably lived. And the answer seemed to be inside these multi-layer perceptrons. So one thought you could have in the back of your mind is that insofar as prediction requires context, this is where the attention blocks are relevant, and insofar as prediction requires just general knowledge from the world, these perceptrons give extra capacity to store some more of that. It's not to say that they can't live in the attention blocks, but it just gives a lot more capacity for that. And that's basically it. It's just those two, but you go back and forth between many different iterations of it. You'll pass through another attention block, pass through another multi-layer perceptron, and repeat over and over. The thing that makes deep learning deep is this repetition of a certain kind of operation many different times. And what you do is you say you're going to flow it through sometimes on the order of 100 times. GPT-3, for example, has 96 different layers. And at the very end, you want to look at just the last vector of that sequence. In this case, that last vector initially was encoding the word was, but the hope is that at this point, it's absorbed so much meaning from its context and absorbed so much meaning from the general knowledge baked in the weights of the network that it's able to make that prediction in the sense that you can apply a certain simple operation just to that last vector that produces this probability distribution over all possible tokens that might come next. It might feel a little bit weird that you're just doing it on the last vector because in the rest of it, you have this big sequence of very context-rich vectors. Well, what happens to be the case is that for the purpose of training, It's very efficient if all of those other vectors are simultaneously being used to predict what comes next at various different points for subsequences of the text that you're putting in. That way, one training example can act like many. And now, I know you know this, but just to keep in the back of your mind, the whole framework behind any kind of machine learning is that rather than telling the network what to do in a very designed sense, where you're going and fine-tuning, okay, I want you to do this with this token and that with this token, you instead just provide a very general framework, and that framework is characterized by a bunch of tunable parameters, just real numbers that you can change, often hundreds of billions of them. And you show it many different examples of the inputs and outputs that you might want it to have. In this case, just random snippets of text, say pulled from the internet, and then what the actual word following was. And as long as you have some kind of procedure that will tell it how it's doing in a particular example, either saying, ooh, you did poorly on that example, you need to change your weights this way, or you did well on that example, you don't need to change too much. Then if you run this through for many, many, many different examples, presumably some kind of behavior emerges within that flexible structure. Now, the reason that's important to keep in mind is that it means actually understanding what's going on is extremely challenging, because it is an entirely separate question from the design of the network itself and understanding what the computations are. What you and I are going to do is mostly focus on what are those computations and what is the framework, and we're going to use some motivating examples of what we think it might do to help learn what that structure is and make it more memorable. But the actual question of what it's doing, in a deep way, is a very, very unsolved one still today. The specifics, if you're curious for how this training will look, at a high level, you have a cost associated with each example. So let's say it's auto-completing a phrase, TNG Technology Consulting is a blank. And from actual snippets of text that it pulled from the internet, let's say one of the examples included the word leading following in there. What you would do is say, what probability did you assign, little network, to the actual next word that it was? And then you take the negative log of that probability, and that defines a cost. So you kind of see the graph here, and essentially what it means is if it assigns a probability closer to 1, that cost is very close to 0. But if it assigns a very low probability, as in it wasn't predicting the word that there actually was, it increases very steeply as you get there. And this is just the cost on one example. In principle, the cost for the entire network is going to be a sum or an average for the cost over the many, many, many trillions of examples that you give it. And so the visual you might have in your mind loosely is that there's a kind of surface where what you and I can graph and show on a screen is limited to something where you have a function who maybe has 2 dimensions of inputs, 2 different numbers as inputs, and then that cost as a 3rd dimension for that output. And that would get you this surface. And in principle, you want to find a low point on it where there's a low cost. But of course, the network doesn't just have 2 different parameters as the input. It would have hundreds of billions of parameters. So it's going to be some super, super high dimensional cost surface. But still, the thought that you have in your mind is that the process of learning involves tweaking those parameters iteratively so that you're taking little steps downhill on that surface. It's not going to be in 2 dimensions, it's going to be in some crazy high number of dimensions. But still, the idea is that you're slowly tweaking it in some way to try to find a minimum on this cost surface. What that means is you really have no idea what behavior is going to emerge with those parameters, because it's whatever emerges on this unbelievably complicated surface and what local minimum it happened to fall into. So that's a thing to keep in the back of your mind. Now, one of the visuals that we can try to get to this comes from something that is very relevant to parsing everything that happens with transformers, but was not at all new to transformers. It existed in natural language processing for a while, which is this very first step where you're associating words with vectors in some way. Now, on the one hand, the reason you have to do this is that if you're doing certainly deep learning, but most categories of machine learning, it's very, very helpful if your inputs and your outputs are both real numbers, things that you can change continuously, because that way you can do calculus and you can do things like gradients. So converting words into something that's expressed in this continuous realm, like a vector space, is a very natural first step for that. But what's very fun is to look at what kinds of patterns emerge as you train the network and as you see what sort of embeddings it stumbles upon for doing whatever task it's trying to do, whether that's next word prediction or something else that presumably requires understanding language in some way. One of the things that will emerge is that words with very similar meanings tend to cluster near each other. So if you look at all the nearest neighbors for a word like tower in a simple word-to-vec model, you get a lot of other words that have kind of these tall construction building-ish vibes. And these are, in some sense, a cluster that represents a loose idea represented in that point in the space. But it gets a lot more interesting than that, because it's not just a matter of where the words are and how they cluster, but also that directions in the space might encode different sorts of meanings that aren't necessarily captured in a particular word, but just a more generic idea. So there's this paper in 2013 from some Google researchers. It's called Efficient Estimation of Word Representations in Vector Space. And they had a number of very memorable examples in there. But one of them that they pulled out was how if you take the embedding of woman and you subtract off the embedding of man, so you might think of it as this sort of difference vector in that space, and then you add that to the embedding of king, so you take that difference and you add it to king, and you search what are the nearest vectors at that point in the space, what you find is that it's actually quite close to the embedding of queen, which is very fun. It's a very mathematical way to basically play the analogy game that would be on like old SATs or things like that. It is fun. I tried to reproduce this, though, by downloading a certain simple word-to-vector model, and it kind of worked, but actually the nearest neighbor to that point was the word king itself. Queen was the second most nearest neighbor. It sits a little farther off, which kind of makes sense because the way that queen as a word shows up in training data is not just a feminine version of king. You have things like the band queen or the word drag queen. But where it worked really well is if I played around with family relationships. So, the difference between uncle and aunt is quite similar to the difference between man and woman, and other things like that. The upshot is that somehow during this training process with this abstract gradient descent notion, it's as if the model learned to associate one specific direction in this space with the notion of gender, in the sense that adding a little vector in that direction to a word can take you from the masculine embedding to a feminine embedding. That's very cool. And there were all sorts of other fun examples they put in there. I think one that stood out to me was if you take Japan associated with sushi and then ask it to associate German with something, it would naturally put bratwurst in there. You can just play this game with subtraction. Now, it's very hard to visualize these things, right? Because we can draw three-dimensional vectors, which are representing lists of three numbers, but these word vectors, in principle, are very high-dimensional. And you can understand why it's helpful for them to be high-dimensional, because if you want to encode concepts with distinct directions in the space, then you would like to have a lot of distinct directions to work with at your disposal. In this case, to take the numbers from GPT-3 as an example, the vectors that we're embedding our tokens to have 12,288 coordinates. So in principle, this embedding space is 12,000 dimensions. So it's very, very big. But I also kind of want to explain why it's even bigger than you might think it is. Like weird things start to happen in higher dimensions. To get a sense for why this might be helpful, you should keep in mind we don't just want these to be encoding an individual word. It's not just the various meanings of a word that might be relevant. What we want to happen as it flows through the network is for these to have the capacity to soak in whatever meaning is relevant from the context. So here, if I take a little bit from the famous Robert Frost poem, The Road Not Taken, and we look at that last part of the passage, 2 roads diverged in a wood, and I took the one less traveled by. The word one would start its life in the transformer simply being embedded to a generic embedding of one that knows nothing other than, maybe it's a number, a pronoun, things like that. Once it has the ability to soak in context, if you want to predict what comes next, it would be helpful to somehow know that it's one of 2 roads, to know the antecedent of that pronoun. It might even also be helpful if you let it flow through the network and get it to ruminate on it more, to somehow encode the more high-level, inarticulable, poetic ideas there, that it's symbolizing choice, what it's a choice between. Those very high-level ideas, if you can embed them in the vector, might be relevant to predicting the next token. And anyone who's interacted with these LLMs often gets the feeling that it really does seem to understand something at a deeper level that's not just as simple as defining one word versus another. And when you think about it from that point, 12,000 dimensions doesn't actually feel like all that much. Like on the one hand, okay, that's a large number of different directions you could work with. But if we want to encapsulate every possible concept just with a distinct direction in this space, well, it doesn't seem like that much to work with. I'll give 2 quizzes here. One is a relatively easy and uninteresting one, and the second one is dramatically more interesting. So quiz number 1 is to ask, if you have a bunch of vectors, how many vectors can you fit into an n-dimensional space so that every pair is 90 degrees apart? The reason this would be relevant, if you want distinct directions in the space to correspond to distinct ideas, if they're perpendicular, that helps you from having unwanted overlap. Like for example, if you have some direction that corresponds to the idea that the words being spoken are in German, and then some other direction corresponding to the idea that the general tone of speech is one of skepticism. You don't want those to align over each other, because that would mean that any time that you're speaking German, it accidentally infers that it must be skeptical in some way. Maybe that one's not a bad idea, but in principle, you want more independent directions. Now with this, the answer for an n-dimensional space is n. This is actually kind of what defines the notion of dimension, at least in an abstract sense, for a vector space. Now, a fact that I didn't know that's a pure math fact, which is very fun and fascinating, until I was talking to some people who do interpretability research into large language models, is a slightly related quiz, which is to say, how many vectors can you fit into an n-dimensional space? Not so that every pair is perpendicular, but so that every pair is kind of almost perpendicular. Let's say you give a little buffer where they can be somewhere between 88 degrees and 92 degrees. If you think about it, if you're just going from two-dimensional to three-dimensional intuition, and you play with it in your mind, it kind of can't fit any more. Like that little wiggle room doesn't give you that much. It turns out, as you scale things up, the way that the answer to this question grows is exponential in the number of dimensions. And I tried playing around with this a little bit. I would actually love if any one of you out there wants to give a numerical answer to this in the case of, say, 1,000 dimensions or 10,000 dimensions. When I was playing with 100-dimensional vectors, I could definitely comfortably fit like hundreds of thousands in that would be quite close to each other in this almost orthogonal way. It gets a little computationally expensive if you try to do it with a 1,000-dimensional vector and hundreds of millions of them. But it's shocking, actually. You can fit very, very many, even though 88 degrees, 92 degrees, to our eye, those look almost orthogonal. And this might explain a couple different things. One, it might explain how these models can actually fit quite a few ideas into a seemingly small space, small in the sense of compared to the number of concepts in the world, 12,000 isn't that big. And also why they scale surprisingly well, because you don't really get this effect of exponential growth kicking in until you get to a certain dimension. And so as you go from, say, 10 to 100 dimensions, it's not just that you're getting 100 times as many directions at your disposal, you're getting many more than that. And as you go from 100 to 1,000 dimensions, again, you get this sort of super linear increase. Now, that's just a thing to keep in the back of your mind so that every time I'm trying to motivate something by saying, oh, imagine some direction in this space encodes such and such idea, even though that's a little bit of a made-up example for the sake of motivating the structure, it's maybe not that implausible to have certain very specific concepts correspond to certain specific directions in the space. So with all that said, let's get into the meat of the matter, which is what's going on inside this attention block? What is the specific mechanism by which information is transferred back and forth between these vectors? And once you do, you can have the sense of what is the number crunching that happens inside a large language model, and why is it as parallelizable as it is? The way I'm going to do this, like I said, is by telling a little bit of a lie, where we're going to imagine something that we might want it to learn. We would hope that it learns. But this isn't to say that it's necessarily what actually happens in production models. Let's say we have got some kind of phrase like a fluffy blue creature roamed the verdant forest. We want to think about how do the nouns in that phrase get updated by the adjectives. And what I mean by that is when you initially encode all of these, because they don't have any notion of their context from the initial encoding, the vector associated with the word fluffy, for example, is just some abstract notion of fluffiness, not tied to anything. Or the vector associated with creature is just some very generic notion of creature that's not going to be any more specific than that. But we want to somehow get it so that these talk to each other and the relevance of fluffiness and blueness gets baked into that creature word. I should say it's not just that they encode the particular word, they encode a little bit of extra information too, which is the position that it shows up in the context. So that position kind of gets baked into the vector. And this is a very important idea because one of the philosophies here is you want to keep everything parallelizable, which means if sequential relationships are relevant, something is right next to another one, you don't want that to have to be inferred from the way that the data is processed, say going through it step by step. Instead, that should entirely be inferable simply from the state of the vector itself, regardless of what order things are processed in. But in principle, each one encodes basically just the meaning of the word, also the position. So at the moment, if we're envisioning it with these little diagrams here, what you would want is that after the attention process goes through and after you do whatever computations we're going to do, the vector associated with that token creature would now encode the much more specific notion of a fluffy blue creature. Or the vector that was associated with that position of forest now encodes a much more specific notion of a forest that has some greenness to it. And the constraint that we have, it's not a hard constraint, but a helpful design choice if you're doing any kind of deep learning here, would be to make sure that all the operations that you're working with to somehow ask the question of which ones are associated with which and how should they update each other are expressed in the language of matrix multiplication. Because if you do that, where you have a bunch of matrices that are filled with tunable parameters, then this process for training, which relies on gradient descent and a thing called the backpropagation algorithm, can work very efficiently. And it's in part because matrix multiplication can be done very efficiently on GPUs in parallel. It's in part because it's a linear operation, and when you're doing calculus with that, the derivatives are nice and simple. There's no added complexity that emerges. So in general, you try to say, how can I somehow express this notion of letting one thing influencing another, only using the language of multiplying matrices, where those matrices have tunable weights in them that can be, hopefully, learning to do what we want them to do. And there's 3 matrices that are going to come up. They're called the query, the key, and the value matrices. And we'll go through them each one by one. But to set the stage, the query matrix is as if you want to let each word ask a question. So you might imagine the word creature, or any other thing in there, asking, hey, are there any adjectives sitting in front of me? Because right now it can't really see its context. It just knows its position, and it knows that it's a noun. And you also want to give the adjectives that sit in front of it the capacity to somehow, numerically or mathematically, respond to it, answering, yeah, I'm an adjective, I'm in that position. Now, of course, they don't literally ask. Instead, the way that this looks is to associate the embedding for that word in creature with a new vector. It's what we're going to call the query vector associated with that token. And this query vector is commonly much smaller than the embedding. So if that embedding dimension was like 12,000 dimensions, a pretty common choice for keys and queries would be like 64 or 128 dimensions. And the way that you generate this query vector is going to be with a matrix. You take some big matrix, you multiply it by the embedding, and presumably it should somehow be able to pick up on, oh, this embedding is for a noun, and it's a noun in a certain position. And the query that it spits out should somehow encode the idea of looking for an adjective in certain positions. The visual you might have in your mind is that if that embedding vector was in this very big space pointing in some direction, encoding all of that, we're mapping it down to this smaller space to ask the question. And this isn't just something you do to one of the words, you do it to every single one of the words. You multiply them all by that same query matrix. And what that would mean is that every time it hits a noun, the query that it produces is going to be effectively asking, hey, are there any adjectives in such and such position sitting in front of it? You might naturally ask, what is it doing to all the ones that aren't nouns? And who knows? Maybe it's trying to do something else in parallel. For the moment, given that we're just making up a toy example to motivate the structure, I can say, let's just focus on the nouns and then talk about all the other things that you might want a mechanism like this to do later, and whether that would be accomplished in parallel in the same matrix or not. So you apply this to all of the different embeddings, you get this sequence of query vectors, and in the same moment, you also multiply them by a distinct matrix, what we're going to call the key matrix, I'll label it as WK, and you produce a sequence of keys. And it's entirely analogous. Those keys are also going to be smaller vectors in that same smaller space. And the way you think about it would be that they're kind of answering a given question. The keys and the queries are trained together so that if a query vector was picking up on a pattern like looking for adjectives before it, the key matrix should be something such that when there are adjectives sitting in a position before it, it spits out something that will correspond to the answer yes. We'll see what that means in just a moment for them to correspond. But like everything that we see, this key matrix is just full of parameters that are learned during the training process. So whether this is actually what it does is a separate question, but the hope is that you're giving the model capacity to do something like this. So if you have all of these keys, and you have all of these queries, and you've trained everything, just hoping that a bunch of data will somehow get these patterns that you're hoping for, you might think of those key vectors in the same way. You've taken something from that very big embedding space, and you've mapped it down into that key query space. And you should think of that smaller space as really being the same one, where the keys and the queries live in the same space. Because what we'll mean by saying that the key is answering the query is that they align in this space, that they kind of point in the same direction. So if you were to take whatever query was produced by creature, asking, hey, any adjective sitting before this position 4, then the key produced by those words blue and fluffy should point in a similar direction, so that you can pick up on the fact that they correspond by somehow measuring whether they point in the same direction. So how do we measure that things point in the same direction? I mean, there's a number of different ways, but certainly in the context of machine learning, where everything is friendly if you can just multiply things and add them up and do nothing more complicated than that, easiest tool in the belt is the dot product. This dot product is going to be positive whenever two vectors align with each other. It's going to be 0 whenever they're perpendicular to each other, which we'll think of as meaning unrelated. And it's negative whenever they point in kind of opposite directions. So if after producing all these keys and queries, you take each pair of them and you take a dot product between every possible pair, this is going to give you a grid of values that's telling you which words are relevant to updating the meanings of which other words. So the way I might like to visualize this is thinking of all of those points inside the grid as literal dots, where the big dots correspond to large dot products, small dots to smaller dot products. So in our particular example with adjectives and nouns, that pattern would look something more like this. Or for example, if we zoom in and you look and you say, okay, Fluffy and Blue each kind of give us something which is, very large when they're being related to the word creature, and then everything else is small in comparison. That's going to be something we can work with, and the question is, okay, what are we going to be able to do with this if you pick up on which words are relevant to which other ones? Now, the thing that we're going to want to do, and there's a certain lingo for this, by the way, where anytime this happens, you say that those tokens on the left attend to the token on the top. So in these cases, the adjectives attend to the creature. What you want to do is take some kind of weighted sum according to how much each of these vectors on the left attends to one of them on the top. And we're going to take weighted sums along the column such that we want the big ones to matter more, and then the small ones with very unrelated words like the down in the row to matter less. But at the moment, these aren't weights. These are just outputs of a dot product that are maybe very large positive numbers or large negative numbers. And if we want them to behave like weights, we need them all to be between 0 and 1, and for them to all add up to 1. And once we have it like that, we'll take a weighted sum. In a couple minutes, you'll see what it is that we're taking a weighted sum of. But just knowing that we want them to act like weights, the tool in the belt for this, another very common function that comes up in machine learning contexts, is something called the softmax. It has a very elegant little formulation. You essentially exponentiate everything and then normalize it. But all you really need to think about is that it takes an arbitrary list of numbers. They could be positive, could be negative, they could even be infinity. And the output is going to be a list of numbers where each one of them is between 0 and 1. And if you add all of them up, it adds up to 1. And the larger numbers from the input will correspond to larger probabilities, basically larger weights in that output. And then the smaller numbers from the input end up closer to 0. So the reason we call this softmax is that it acts kind of like a maximizing function, where if one of those numbers in the input was notably bigger than the rest, then the distribution on the output has almost all of its weight towards that. So if you were sampling from that distribution, it's effectively the same as just choosing the maximizing input. But it's softer than a max in the sense that as you continuously change things, you get this smooth change in what that output is, which again is friendly if you want to be doing calculus with this, which is what's going on with that gradient descent under the hood. So we take this list of numbers that we want to act like weights that are currently just arbitrary things between negative infinity and infinity, and you run it through a softmax, and you do this to every single column in this diagram. So every column that corresponds to one of the queries, you're taking the softmax with all these dot products, and it's giving you a sense of weights for which other words are going to be relevant to updating the one at the top of that column. There's a little nuance that I'm not illustrating in the diagram here, where before the softmax you divide by the square root of the dimension for that key query space. Doesn't really matter. It's something that's helpful for numerical stability, but if you're curious, that's a little detail missing here. So once we have this grid, this is properly what I'm going to call the attention pattern associated with this. Well, it's actually not an attention block, but just ahead of that attention block. And this attention pattern, again, I kind of like to visualize with a bunch of dots, just giving you a sense of which things are most relevant to which other things. But there's one tiny more nuance that we need to address before we actually use this to make any updates. And it has to do with something I referenced a little bit earlier, for how during training, there's not just one prediction that takes place, but actually quite a few different predictions as it processes a given input. So here, if it's taking in the phrase, the fluffy blue creature roamed the verdant forest, and predicting the next word, as it all flows through the transformer, what comes out on the other end is going to be a prediction at every single step along the way for every different subsequence of tokens. And again, this might not seem super relevant in the case of something like a chatbot where it's generating text. Like, why are you predicting the next word? You already know what the next word is. But it's very relevant for training, because it means that if you feed in this particular thing, rather than just having one particular training example, which is whatever actually follows this, you get a whole pile of training examples where it's using those same weights to try to make predictions all along the way. And so all of the weights get to be updated by all of the different predictions that it's making for that one bit of processing. And the context can get quite big. It can be thousands of different tokens. So that can mean the difference between a single training example and thousands of training examples for one particular run. Now, if this is going to work, if you want to be able to get this training efficiency speed up by having it do all of this in parallel, it means that even though it's processing the full block of text, for example, here, if it's saying, the fluffy blue creature blank, and it's predicting what, verb might come next or what word might come next, it has to somehow ignore the fact that it already knows, because that's in the input, the word that comes next. And given that the attention mechanism is letting all the vectors talk to each other, if you just blindly let it allow all of them to talk to each other, each one along the way would have the answer given away to it. So what you have to do is take all of the positions that correspond to later tokens influencing an earlier token and do something to zero them out. So in this case, everything where there's a later token, like the word roamed, sitting before an earlier token, like the word creature, that's something that we're going to want to make sure is 0. And by the way, if you see diagrams like this in other sources, there will be different conventions on whether people are putting the queries at the top or the keys at the top. And so you might see this masking look transposed from where it is now. But just as long as you think about the influence of it is that you don't want to let later tokens influence earlier ones. You have to set those to 0. Now, if you just naively set them to 0, the problem is that your columns wouldn't be normalized anymore. So given that we want to use them as weights for a weighted sum in a moment, that would mess things up. You could say, OK, well, then just set them to 0 and then renormalize the columns. But another way to do it that is a little bit more elegant, before applying the softmax, set all of those values inside that masked region to -infinity. And this feels a little bit weird if you haven't spent a lot of time with softmaxes, but the effect of that is that any component that was -infinity, after you pass it through the softmax, goes to 0. And then automatically, because the output of a softmax always adds up to 1, the columns are going to be normalized in this way. So this gives you what you would call a masked attention pattern, or sometimes people will call it causal attention, causal self-attention, because you don't want to let later things influence earlier ones. Now, a thing you might think about in the back of your mind at this point is, just at this point, creating this attention pattern that determines which tokens are relevant to updating which other tokens. As you increase the context size, which is how much text it's incorporating into its prediction, this pattern that it's producing grows quadratically with the size of that context. So this is why it can be very non-trivial to just take a traditional transformer and simply scale up the context. So anytime you have some of the newer large language models with very large context windows, they have to be doing something a little bit cleverer. They have to have some variation on the original attention mechanism. And another thing you might pause and ponder on here is, even though it is a very large pattern that you're going to get as you have very large context sizes, when you're going through this process of some large language model producing new text, doing it one token at a time, you might notice that there's going to be a lot of redundancy in each one of those computations. Because remember, in principle, for each one of those tokens it's generating, it goes through the whole process where all the data flows through this network and does everything that we're talking about here for each one of those tokens. But because a lot of them are the same when it's generating new text like this, there is a lot of redundancy, and you can have a lot of clever caching to basically take advantage of it so that you're not faced with that quadratic speedup at inference time. It's something that's much more relevant during training or during the very first pass when it's making its very first token. Another thing you might want to reflect on, that question from earlier, where I said, why don't we just break up our input into characters? Why aren't tokens just characters? Because that feels like a much more natural, atomic unit of what text is. A couple answers here. One of them would be the context would just be much bigger. And given that scaling with context involves scaling quadratically, that can bloat your network very fast. Another one would be that as you embed these tokens and you want them to embed some notion of meaning, if they're just going character by character, it has to get processed by the first couple layers of the network before it could possibly get in the meaning of the relevant words. Whereas you let it just kind of jump directly to the meaning of words from that very first step if you do it at tokens. There's a balancing act, though, because you can't make the tokens too big because you want them to be something that shows up sufficiently in training data that you can learn from it. If your tokens were like paragraphs, each one would only show up at most once in the training data, and you would hardly be able to learn anything from it. So the pattern that people have found that seems to work quite well is something called byte pair encoding, if you want to search further on it. But in the back of your mind, you just think of it as words, pieces of words, punctuation marks, things like that. So, given that you've figured out, or the model has presumably figured out, which words need to be relevant to updating which other words, the question is how that actually happens. How is it, for example, that the embedding of a word like fluffy talks to the embedding of creature so as to somehow update it to point in a more specific direction that encodes the notion of a fluffy creature? Simplest way to do this is just throw yet another matrix at it. We're going to call this the value matrix, and it's going to be something where if you multiply it by, say, a given adjective, the value that it produces, this new vector that it produces, is something such that if you add it on to a given noun, add it to the embedding of a noun, it will point that noun in a more specific direction that also encodes whatever the relevant meaning of that adjective is. So in this case, it might add a certain fluffiness direction to the word for creature, but if you multiplied it by something like blue, then it would produce a new direction such that if you add that onto the result, then you would be pointing in an even more specific direction. It's of a fluffy blue creature. You could do this. This would actually work perfectly fine. But if you look at the number of parameters involved here, because those key and query matrices were mapping to smaller spaces, if we take the numbers from GPT-3, each one of them ends up having about 1.5 million parameters. But with this high dimensional embedding space, if the value is mapping from the embedding space to the embedding space itself, it involves almost 100 times as many parameters in it, which could be fine, but it's a little more elegant, and then it works more nicely with how this all plays out in the context of multi-headed attention, which we're getting to in a moment, if that value map is actually broken up a little bit and involves fewer parameters, where first it maps down to a smaller space, and then it maps back up to the bigger space. So still, overall, it's something that takes in these 12-dimensional things and spits out some other 12-dimensional thing, but for the linear algebra enthusiasts among you, you might think of it as a low-rank transformation, or just at a high level, it's something that devotes fewer parameters of the network to this task. So when you have this value map, you're going to multiply it by each one of the embeddings in the same way that you multiplied the key map by it to get a bunch of keys. And sort of associated with each position of that key, you have a given value. And what we're going to do then is take weighted sums along each column, weighted according to the attention pattern, and the thing we're taking sums of are these values. So for example, in the column we have associated with the word creature, almost all of the weights after the softmax are going to go to 0, or something that's effectively 0. And the only other tokens that actually attend to it are the adjectives. And so what we want to do is take a weighted sum of those two adjectives while everything else is zeroed out. And once we add all of those together, that's going to give us the change that we want to make to the embedding up top. So this will produce some change. I might give it a little name like delta E. And then the thing that will pop out of the attention block at the end is going to be whatever the original vector was that came in plus this change. And that change is this weighted sum along the column. So the hope is that for this kind of example, it takes something that encoded creature, and then it spits out something that encodes a more specific direction of that fluffy blue creature. And this isn't just doing it to one column, it actually does it to all of the different columns based on the attention pattern, based on those different values. It'll take this weighted sum, producing a sequence of changes. It'll add that sequence of changes to the sequence of vectors that flowed in, and those sums are going to be what flows out of the attention block, at least almost. So this, so far, I've just been describing what you would call a single head of attention. And as it is, this is actually quite a lot to think about, because each one of them is being multiplied by a key matrix and a query matrix and a value matrix, and those keys and queries are producing this big attention pattern, and that's going through the softmax, which is used for, it's a lot to think about. But this happens like 10,000 times for a single pass of the network, because this is just a single head of attention, and then each attention block often involves many different heads. It might be something on the order of 100. Bigger models could have bigger ones. And then there's going to be many different layers of attention. So if this is just one of the heads, multi-headed attention is something where you would think about those happening all in parallel. And again, the mantra for transformers is that they're very well architected to work on GPUs so that you can run these things in a shorter amount of time, even if it's a greater amount of computation. And what I mean by multiple attention heads here is that this adjective noun example is just one out of many, many different ways that you might imagine context is relevant to updating meanings. You can imagine all sorts of other things, like also in the sphere of grammar, adverbs, updating the meanings of verbs, or nouns and their antecedents going together. But it doesn't even necessarily have to be grammatical. Just really anything where you want to somehow transform information that was in one part of a passage to something that's later such that it's relevant for predicting the next word. That has to somehow happen through these key query and value mechanisms that are asking which things are relevant to which other ones and what changes should take place when that relevance is there. So each one of the heads inside one of these multi-headed attention blocks has its own distinct key and query matrices, which are used to produce their own distinct attention patterns. And they have their own distinct value maps, which are producing their own distinct sequences of values, which again, you do this whole weighted sum along the columns for. So it really is a lot to think about. And every single output from those heads, which is a proposed change to make to the embedding that was in there, you add all of those up together to the original embedding that flowed in. So there's lots and lots and lots of different things that are added to it, or at least potentially added to it, depending on whether they're zeroed out by these attention patterns or not. And so in this just little schematic illustration that I gave, where we have an attention block and just some dancing lines to indicate that they're talking to each other, the thing that's happening under the hood there is all of those distinct attention heads, which themselves involve all of these distinct patterns playing with each other. And like I said at the beginning, there's not just one attention block. It flows through a multi-layer perceptron and then another attention block that again lets them all update each other and just keeps flowing through like this. And so the loose thought there is you have all of these vectors gaining richer and richer meanings, and the context that they're drawing from is itself becoming richer and richer and richer. And by the end, your hope is that it's not just the meaning of the original token anymore. It's really whatever it needs to be able to predict what comes after at that point. Now, there's definitely a lot more that can be said about transformers. We could, for example, dive into what's going on with those multi-layer perceptrons. But I think this is a pretty good point to step back and ask a little bit, why are these as effective as they are? There's lots of different tactics that people have been trying in deep learning for a while. But essentially, since that 2017 paper, transformers have just been on the uprise for being applied to more and more distinct fields. And there's a couple things you could point to here. One of them is that a big lesson in machine learning through the last couple decades is that scale alone matters. Simply making things bigger and simply giving them more training data can sometimes give qualitative improvements to the model performance. And there's laws that people will write about this. They're not mathematical laws, they're more kind of heuristic laws, but they can be phrased mathematically that predicts for a given size of the model, for a given amount of training that you do, what's the cost function going to look like? And if that cost function is going down, that typically corresponds to improvements in the model performance that are qualitatively visible. It just looks like a chatbot that behaves better, things like that. And if scale matters, that means that parallelizability matters. So a lot of earlier natural language processing, it would read through text the way that you and I do. It would kind of start from the beginning and go through the end, and as it's reading through, it updates meaning a little bit more. But once people did away with all those mechanisms and just left one of them, the attention mechanism, which allows things to talk to each other, but not in a way that relies on sequential processing, it means that they can process text very differently from how you and I do, where they take in the whole passage and just kind of ingest it at once, letting all of the different embeddings talk to each other as it does. That's very weird from our standpoint, trying to empathize with it compared to how we do it, but it's extremely friendly for GPUs and letting a training run effectively do more total floating point operations in a given amount of time. The other benefit here, the fact that we're doing a next token prediction, that means that you can train on a huge amount of data that doesn't require human labeling. So having this pre-training phase where you can just give it massive amounts of data that didn't require having a bunch of human labelers labeling what's on an image or things like that, means that you can get a lot of that training reps in this very large model without being constrained by the human feedback. Human feedback usually comes in later, where often the reason that we call it pre-training when you do all this next token prediction is that what's required to make chatbots, for example, work more effectively is to have some kind of reinforcement with humans in the loop thereafter. But still, the idea that most of the actual flops in training can come from something unsupervised plays into this idea that scale and scale alone tends to matter. And another component for transformers, which is quite nice, even though we were focusing on language, where you break tokens into, or where tokens are little snippets of words, the fact that you can tokenize essentially anything, just break up whatever your data type is into little pieces, and then embed those as vectors, means that you can have lots of distinct data types work in conjunction with each other. If you want a model that processes not just text, but text together with an image or together with sound, it can treat all of those as equal citizens in the same landscape, rather than having to have different bespoke architectures for each one and then having a whole different process for how they talk to each other later. So with that, I think I'll call it an end here and say thank you and turn things over to the Q&A. I'm more than happy to talk more about transformers if you want. I'm also happy to answer anything about 3-Blow and Brown if you want. But with that, I'll call it an end. Thanks.
I've got one question. I've also seen your videos, so you seem to work quite some time on this topic already. And I would be interested how much work you put in the last month or year or whatever into this topic.
A lot more than I was expecting, but it's been fun, especially because I'm more of a math person by background. It's just involved a lot of talking with people who know more than I do on the matter. And I've been especially fond of the interpretability researchers on this front because, they're motivated to understand what's actually going on. From my point of view, I'm like, I don't care if that's what's actually going on. I just want like a good pedagogical motivation for the structure. But it's also thought-provoking in its own right, trying to say, how can we probe at these models? So, one of the things I would love to talk about more, would have talked about today, it's just very hard to fit in because you need all the background. It's just some of that work that's done to try to say, that little fact I referenced, for example, where the number of vectors you can fit into a space that aren't orthogonal but almost orthogonal, scaling exponentially. This is related to something they'll call the superposition hypothesis. And there's very clever ways that you can try to probe at what those feature directions might be, even when it's many more than the numbers of dimensions. And there could be a whole video about that. And so there's been a number of rabbit holes like that, which may or may not actually turn into videos, but I'm quite happy to do. And then the visuals are, it's a labor of love always to pour time into those and try to get something that communicates what I want.
Got a question here?
Yeah, thank you for the inspirational talk. I have a question regarding transformer models. It's a bit technical. So this trend of using deeper and deeper transformer models remind me of the good old days with convolutional neural networks, where they hit a barrier in terms of exploding and vanishing gradients, where they started using things like residual networks to let the signal pass through without any transformations when not needed. Are there similar trends in transformer models that you're aware of?
I'm not entirely sure I follow the question. So you're saying that the trend where residual networks, for example, came to be quite helpful. Is there something like that in the case?
Yes.
The residuality is sort of baked in from the beginning with how it's even done. The thought that as you're going from layer to layer, rather than generating an entirely new data type, you're kind of adding to whatever there was before. So it's not just in the sense that you're preserving the dimension so it's friendly for the machine, which seems to be one thing that's in the consideration. The people who designed it are very hardware aware, in contrast to maybe some other machine learning frameworks. But there seems to be a continuation of the trend that you're referencing there, where making things residual is deeply, deeply helpful. And whether that's because it makes for training stability or whether there's something more conceptual, I kind of can't say. But it definitely does seem to be the trend.
We have another question over here. Hey, thank you for the great presentation. So when it's a very long presentation or a very long talk, do you have some metrics that you keep track of, as in how many jokes should go into this 10-minute period to keep people awake? Or do you have like a team of creative thinkers per se that kind of arrange everything this way on the background for it to be finalized by you in the end?
Oh, to have a team. No, I don't think I'm very good at that, actually. Like, I'm sort of a nerd who just digs into the topic itself and says, all right, let's just dig into the topic. And the thing that should motivate the next step is centered around understanding and clarity rather than humor. So there's certainly not enough deliberate thought that goes into that component. But for me, I think what I find most motivating in learning something is just the promise that I'll actually understand it. And so I think the way I try to motivate audiences with, say, a longer video is not so much that in the middle there's going to be an unrelated joke to crack, but more just that there's a real promise that, like, hey, we're on a path to understanding here. And insofar as that promise is something people believe, I think that's when they stick with it a little bit more.
A question from behind?
If I understand you correctly, you use GPUs to do a lot of transformations, but you're not really interested in the absolute values that you calculate in each transformation. Wouldn't be the mix of analog computers together with digital ones resolve this energy hungriness?
It's a good question. I am not an expert on that, the drawbacks or advantages of analog computers, and therefore I should stop talking now. But in principle, like from a first principle standpoint in physics, it does make a lot of sense where if you're more error tolerant in that way, like the big advantage of digitization over analog computers, if you were to go back to the 1940s and explain to someone like why they should bet on one horse and not another, has to do with error propagation. And so in this case, if you kind of don't care about that because everything's just a matter of soft association anyway, I'll believe it. I am as curious as you are to understand why that's not the case. My best guess, or why they haven't, like replaced it, is just that there's so much smart mind power that's gone towards optimizing the living Christ out of matrix multiplication in a digital context that it's just hard to catch up with that, even if something's going to be better from like a first principle standpoint. There's such a head start on that one. But if you find someone with a clearer answer, send that answer my way because I'm as curious as you are.
So we have a question in Zoom.
No, we have one more here.
Good. Yeah.
Yes. Thanks for trying it 3 times to come here and actually doing it this time. My question is about tokenization in images you briefly mentioned. And text and sound are basically one dimension in some sense because you read from left to right or you listen through time. But images are inherently 2-dimensional, and I would argue that the pixels above and below are more important than the one at the end of the current pixel row. So how could you tokenize that into a nice...
Yeah, so I guess there's 2 things there. One is the tokenization, and one is how the attention will work there. I mean, the tokenization, loosely speaking, you'd want to think of it as like little patches of the image are going to be the tokens, and then you have some notion of positional encoding that will encode that, but not just the X position, but also the Y position, so that the vector that embeds that patch kind of knows where it is and can use that for associations. But as I understand it, the naive way of doing that, you're just going to end up with either way too many tokens or tokens that are way too small, because if you think of kind of the resolution of an image and wanting tokens to be ones that like show up decently often, you would just end up with something that bloats the network a lot. So you have to get a little bit clever, but like in principle, it's just the patches. And then for how they talk to each other, there's various different things where you can mask the attention so that it first does it column-wise and then does it row-wise or something like that. But there's, as I understand it, like not one single way of going about it. But in all cases, it does do something that appreciates your point where it's 2-dimensional. And the way that you'd see that is usually in the positional encoding.
I think that was the last question.
Okay.
Grant?
Thank you very much, everyone, for coming. This is delightful to actually be here.